Well, welcome everyone. For those of you who are not at Cambridge, you won't appreciate that it is raining hard here, and we all have to battle in through rain, which has an official yellow rain warning, which is splendid. Anyway, for those of you who don't know me, I'm Chris Budd. I'm one of the participants in the Maths for DR program from the University of Bath. Our speaker today really does not need any introduction. If you don't know Carola, what have you been doing with your life? Everybody knows Carola. This is Carola-Bibiane Schönlieb, who is one of the organizers of this program, professor of mathematics here at Cambridge, and she's going to tell us about deep learning in inverse problems. Carola.
Thanks a lot, Chris. Thank you very much. Thanks a lot for coming, everyone, online, and also the physical participants, because it's really super heavy rain here. So thank you for traveling through rain. Okay, so I will talk about how to use deep neural networks to solve inverse problems, and in particular, how to use them to derive meaningful regularization for solving inverse problems. Let's see if it works. Yes, good. So before I start, I really would like to acknowledge all the wonderful work that has been coming out of the Cambridge Image Analysis Group. The team here in Cambridge, without whom nothing that I'm going to tell you about would have been possible. So thanks a lot to all of them. And of course, also to all the funders who are sponsoring us. Okay, so main messages of this talk. First of all, I have really been quite fascinated by the capabilities that deep neural networks have in the context of inverse problems in the last couple of years. And the two main reasons for that are, first of all, that neural networks are very good in expressing information structure in data, and we can use this to our advantage when solving inverse problems. So high quality solutions through data adaptivity. And the second one is that for all of us who are used to solve nonlinear PDEs and non-smooth optimization problems for solving inverse problems, usually might appreciate the fact that once the neural network is trained, it's just an explicit kind of a concatenation of explicit nonlinear and linear operations, and so is much cheaper than what we usually do to solve our inverse problems. Where the call is towards us, let's say, for finding out how to use deep neural networks for solving inverse problems is really that they only make sense. Actually, I should probably not use the pointer because the online participants can't see it. So they only work in practice when they are combined with mathematical and statistical modeling. So deep learning as a hammer, as it really works very well for problems in computer vision and so on and so forth, does not work. You really need to put some prior knowledge, some understanding about the inverse problem you want to solve into your solution. The third point goes a little bit against this. So in general, most of the contributions that have been made in the last couple of years actually do not go this route, and they are therefore not really exploiting the problem structure to actually say a bit more about solutions. What we are always really worried about with inverse problems, since they're ill-posed, is to derive meaningful solutions. And for this, we need to prove certain things like existence and uniqueness, or, and in particular stability with respect to perturbations of the input data. And this is really something that we need to also pay attention with deep neural networks, where we know that neural networks like to do funny things and possibly invent new structures and so on that are not explained by the data. And the last point is really what I want to focus on, the niche, let's say, within this deep learning for inverse problems that we have been working on, which is combining neural networks with variational regularization models. And so this is what I'm going to show you. And the bold statement is that I believe at the moment they're really the best compromise between empirical and theoretical performance. All right, so actually most of the people who are here know this. So I will very briefly jump over this slide. I'm going to look at inverse imaging problems where I'm measuring some data Y that is explained through a forward operator, a linear or nonlinear operator, capital T, applied to the unknown, and in today's talk, image U, that is in addition corrupted here in this, how I'm modeling it here, through additive noise. So little n just stands generically for random corruptions in the data. And so the task now is given Y to compute U, and the typical forward operators that we are looking at in imaging are transformations of the image into another domain, into another space. So from the physical domain, like in the case when the forward operator T is the radon transform or the X-ray transform, to the space of line integrals where the parametrization is not with respect to X and Y, but with respect to the angular position of the line and the y-intercept of the line that you are computing the integral over the image intensity function over. And so I really encourage you, if you want to know more about this, but again, looking at the audience, all of you know about this, that to look at really very educational videos and explanations by somebody who explains everything about tomography. So one thing, maybe looking at this for one more second, if we want to use deep neural networks to solve such problems, one obvious difficulty that we see is that we need to, in order to compute U from Y, we need to change really spaces. We need to go from one very different space to the space of images. And that is, in this case, a global transformation. So in order to do this purely by a deep neural network, you would need to be able to capture this global transformation, which in the neural network language would mean you have fully connected layers, so full matrix multiplications that should represent this. And this is super costly to train and everything if you want to solve very large problems. So it's not trivial. And the other one is, of course, that inverse problems are usually ill-posed. And again, I'm going to jump this, but the ill-posedness, of course, also means we need to be careful how we are going about solving these problems. In particular, we want to prove things like stability of solutions of whatever method we are coming up with to solve this problem. So starting with, I said the model that I want to connect deep neural networks with will be a variational model. And so I'm going to explain this to you now, where variational models pop up in inverse problems as a way to turn this generally ill-posed problem into a well-posed one by adding additional information to the problem in terms of regularity of the solution, and then capturing all of this within a variational model. This is basically the idea. So again, I'm starting with the problem statement. This is the problem I want to solve. And as we have just seen, this is not so easy to do. So what we do is we are going to try to approximate this with another problem we want to solve, this variational problem, where we, in addition to the problem statement at the beginning, we add regularity information about the type of use I want to compute to the solution procedure. And so this comes in this form. So I'm capturing a solution U to my inverse problem as a minimizer of an energy function that consists of two terms, usually data discrepancy term, that in the simplest and the most common form could be a least squares fit between the data and the forward model. And balanced with that, a regularization term that now encapsulates all this prior information you have about the type of use you want to compute. And that is also the one that turns this ill-posed problem in the ideal setting into a well-posed one, at least into one where solutions exist and where you get a certain notion of stability of solutions. And sometimes if you choose this regularization appropriately, you also get uniqueness. And then you balance the two terms with a so-called regularization parameter alpha. That's a positive scalar that that determines how closely your solutions should stick to the data. So how well actually your forward model is explaining data, and that will depend also on how much noise you have, how much you're weighting this against the need for regularization, against damping, noise, and random corruptions that you have in the data. And the typical choice for this regularization functional that is, I would say, the most common regularization function used in particular for inverse imaging problems is the total variation. That is the L1 norm of the gradient of U, if you look at it in finite dimensions. Or indeed any kind of sparsity promoting regularization where you put your prior information you have about U in the form of saying my image U can be sparsely represented by whatever representation. Yeah? And in this case, it's a gradient representation, but there are also examples like wavelets and shearlets and the Sigitter here and so on. Yeah? So this is the typical thing. And this actually works quite well. And you can also see that the regularization has actually, particularly the choice of regularization has a significant effect. So this is a simulated example for image denoising. So in this case, the forward operator capital T is just the identity, just for illustration purposes. I start out with my noisy image. This is my little y now. And I compute the denoised image now via this variation regularization problem with two different choices of the regularizer. One is this total variation regularization that I've been alluding to before. And the other one is for, mathematically and also computationally somewhat nicer choice, the H1 semi-norm, which gives you this type of solutions. And so you see that the choice of this regularizer really determines a lot the qualitative properties of the image that you're here, an example now for CT reconstruction. So going back to where the forward operator capital T can be modeled via radon transform. And again, in this case, you see that this is simulated again. So you have the ground truth. You are simulating, in this case, measurements, radon measurements that are first of all noisy, but that you also undersample in the angular direction. So you have sparse. This is a sparse tomography example. So if you reconstruct without regularization, basically, which would be given in the inverse problem setting by computing the pseudo-inverse. In the CT case, this boils down to computing the filtered back projection, then you get results like this. And if you put in regularization and solve this inverse problem via a variational model, you again see this total variation, typical structures that you get in the solution. Now, if you compare this, of course, with the ground truth image, or even in a way, you compare it with a filtered back projection image, then you might say this is okay, but it's definitely suboptimal. Yeah? So even so even taking into account the idempotency of the forward operator, if you look at the filtered back projection image, you probably would be able to draw yourself a better reconstruction kind of than what you see here in this blocky type of reconstruction. And the reason is just, and this is just for the total variation shown now, but it will be a similar story for any type of handcrafted regularizers as the sparsity-promoting regularizers. There is a limited amount of modeling capacity that we have. And this is just making this point again that so somehow we have this limited modeling capacity. And the question now is how to change this. And one stream of approaches, one stream of attack that people have thought of is changing from this handcrafted type of modeling to a data-driven modeling, where you determine the type of regularization through training data, through looking at lots of images that represent similar structures as the one you want to see in your reconstructions. And in a way, again, it makes sense to do something like this, going back again to this thing that our brain, so we might be able to actually denoise the cameraman much better than the total variation regularization, since we know that this should be grass, and we know some properties of what the fine details might look like in the ear and so on, and in all the details of the cameraman. So somehow it makes sense to think like this. And the starting point of the presentation was that deep neural networks might be quite good to extract structure information from data. And so this motivates looking at deep neural networks for doing this job. And this was indeed what motivated us. And this actually works. And this is just a teaser of saying, this is again the same example as we've seen at the beginning, computed tomography with TV regularization. And here you can see solutions of 3 different types of deep learning-based approaches for solving this inverse problem. And I mean, all of them, I would say, look better than TV. So there is something that we're able
to. So just go back to that. So AR-LPD and AELPD are the different deep learning approaches.
Yeah, I was not so these are just at the moment. It's enough to just know that the 3 examples at the bottom are 3 different deep learning based solutions to this problem. It doesn't matter at the moment what they are, but just to say there is something that that is interesting here. Okay. So how have people looked at using deep neural networks for solving inverse problems? And I always like to categorize this into 4 different paradigms. And the one that is highlighted in red is really the one that I will talk about. But just very, very briefly, the first category, the fully learned models, means you represent the whole process from the data to the reconstruction by a deep neural network, and you don't put any information about the actual forward operator or anything inside that. So you parameterize everything with a neural network. So these are limited because of the reasons that I've said at the beginning, because these forward operators are global operators. The neural network needs to learn a lot when you just make everything data-driven, unnecessarily in a way. Learn post-processing means that you first do a very simple inversion, like the filter back projection we have seen before, and then you train a neural network basically to do an after smoothing of the solution. Yeah? So that's learned post-processing, and learned iterative schemes, or what is also called learned unrolling, means that you take a variational model and its iterative solution as an example, and you so you roll out your variational model into, let's say, 10 steps. You do 10 steps to minimize a variational model, but then you forget about the variational model and you say, I do these 10 steps, but now I parameterize these 10 steps with neural networks. And I let all of these steps do something different depending what is best. Yeah? But the nice thing about these learned iterative schemes is that they capture through this initial thing that you are rolling out a variational model, they capture some structure from the inverse problem through the forward operator being in there and so on. Yeah? And the last one is learning the regularizer, and this is really the one that I will talk about now. And I apologize, there are lots of works actually in this on this topic now of inverse problems and deep learning. So this list here is not at all exhaustive. It should just give you a first flavor of what is happening in this area. Okay, so the learning framework that I will focus on is learned regularizer is I stick to variational models, and the initial reason for that was that I thought variational models we know how to handle. We can put the mathematical, a well-posed mathematical framework around that. The only thing we need to be careful about is if we make certain terms in this variational model data-driven, that we do that in a way that collaborates with the theory. And then the idea is to really use the learning only for what we know we might want to improve upon, which is in our case the regularization. So this is the setting. So we start with a variational model, and what we want to make data-driven, or in particular represent as a neural network, is this regularizer R, which has several advantages. We keep it here. We use the neural network really to capture prior information from data. If we do it right, as I said before, we can prove stability and convergence results for the solutions of the variational problem. We can also, to a certain extent, and Sebastian Lunz, who has been really the one who started all of this in the group, has done a lot of experiments in his PhD thesis where he shows that you also have some flexibility with respect to the noise level. So you can train one regularizer and then apply it to several noise levels. And you still have this tuning parameter explicitly in here. We explicitly incorporate the forward operator here. So this capital T. And at least in this current form, since we only learned the regularizer, we also still have a hand on modeling the noise statistics through the data discrepancy term. Yeah, because depending on the noise statistics, you will choose different data discrepancy. And maybe one more thing to say, although you have probably already spotted this in the setting where we are learning the regularizer, we are going to look at linear inverse problems. Yeah? So where the forward operator T is a linear operator, like in computed tomography, or at least our model for computed tomography.
I'm a bit confused. You've got alpha and R.
Yes.
Are you saying you give it alpha and it learns R? It seems a bit strange that you separate the two if you're learning.
So the reason is we actually separated that on purpose.
Okay.
So we want to learn a kind of normalized R.
Yeah.
And then tune the regularizer to the regularization to the noise level via this regularization parameter alpha.
Using some sort of other method like an L curve or something.
Like an L curve or discrepancy, or the typical kind of inverse problems things. Yes.
So do you learn the regularizer with image data or with measurement data?
Yes, I'll show you now.
Yeah. Okay. So there's
Actually,
still.
I should come to the point because this is what I should talk about, right? But very, very briefly, before I talk about what we were doing, of course, when you start this kind of thing, you think you look what other people have done to learn regularizers. And a lot has happened even before neural networks. People have thought about how to make regularizers more data-driven, just because it's really conceptually quite a natural idea, right? And so one range of works is this work where we look at the class of sparsity-promoting regularizers, but we make the dictionary or the representation in which the solution should be sparse data-driven to a certain extent. And in the sparse coding dictionary learning business, it's done like this, that you write down your solution as a linear combination of dictionary elements, phi i's, so functions phi i's, with coefficients gamma i's. And then the sparsity promoting regularization comes in by saying that very, very few of them are actually important to represent the solution. Most of these coefficients should be 0, and this is represented here through an L1 norm on coefficient vector alpha. And in dictionary learning, basically, so just if you would just have given phi and just optimize over gamma, then this would just be sparsity promoting regularization. But if you also now make phi an unknown of this, this would be dictionary learning. Yeah? So you also learn the phi i's that you parameterized in a certain manner. Another type of data where data-driven regularization also has been coming in is through the plug-and-play framework, black box denoisers, or regularization by denoising, for instance, where you represent your regularizer through an image denoiser. So you learn, you take, for instance, the typical image denoising approaches like BM3D or something like this, and you use that to define your regularization. And there are lots of works which actually show that if you constrain the class of denoisers appropriately, then this actually defines this actually defines a proper regularization. Yeah? So this is another idea. Here, the main idea is that you really take advantage of the fact that a lot of work has happened to do good image denoising. And so there are really very, very impressive image denoisers around. And again, you can think of having a denoiser that is data-driven. Yeah? So this is what makes this basically data-driven. Another range of approaches that also we have worked on for many years is bi-level optimization. And here, the idea is that you take a variational model, you parameterize your regularization functional with, well, usually these are very low-level parameterizations. The simplest one could just be a linear combination of different regularizers with weights in front. And then you learn the optimal combination, the optimal instance of this parameterization represented by an optimal lambda vector of weights lambda, let's say, through a bi-level optimization approach where you minimize an evaluation criterion, a cost functional that evaluates the solution U lambda coming out of this variational model with respect to the parameter choice lambda. Yeah? So you optimize that. And that actually, many people have worked on this, and it's something that is super interesting, both mathematically, also numerically, and also in its application. Actually, you can show that this can give you really much better results than tuning things by hand. The only bottleneck of all of this is that you really need to solve this bi-level optimization problem, which is computationally quite tough most of the time. Now, all of these, maybe apart from the black box denoiser, because you could also take a neural network here, for instance, as a denoiser, are rather low-level parameterizations. And so what we were interested in is really the context where you have very, very rich parameterizations like deep neural networks as regularizers, and see how far we can go there. Okay, and this is now joint work with several people also in the program. So Marcello Carioni, who is a postdoc in Cambridge, Søren Dittmer, who is a postdoc in Cambridge and Bremen, Sebastian Lunz, who has been a PhD student with me, and as I mentioned before, was the one who really started all of this with his PhD thesis. Shubho Mukherjee, who is, I would say, the main person behind this research program around learned regularizers now in Cambridge, as a postdoc here. Ozan Aktem is a colleague of mine from KTH Stockholm, and Zach Shumyalov has been, or is still, an undergraduate student in Cambridge, who has been exceptional, really. Okay, and so the learned regularizers that we've been working on, we called learned adversarial regularizers, and I'm going to now show you how they work. And I mean, maybe I should have said this at the beginning, but please interrupt me if there are questions. I think I'm probably even too slow because all of you know this already. So yeah, but yeah, you can also say speed up. Okay, so how do we train the regularizer? How do we make it data driven in a way? Yeah? So when you make it data driven, the question is, how do you use the data to determine an optimal regularizer? So what is the criterion? What's your strategy to train the regularizer something meaningful? And in our case, we decided to go for a strategy that you can think of as almost like a classification of your solutions into the ones that you, into the ones that that you want the variational problem to promote, you want the regularizer to promote, and the ones that you want the regularizer to attenuate. And this is here described as a data set. We're going to construct two data sets with which I trained a regularizer, the data set of the good guys and the bad guys, where the good guys are the ones for which the regularizer should be small. So these are clean images, let's say. These are, you could think of in the CT context, it could be just very high dose CT reconstructions, for instance, or in the image denoising case, since you have anyway lots of images, these are just clean images in a database that you have. So these represent all the good structures you want the regularizer to promote. And then you also train a regularizer with a data set of the bad guys. And these are basically the data set of these you construct through taking the typical data that you want to take as an input to your inverse problem, and then use an inversion method, a reconstruction method that you want to improve upon, okay? That you want with the regularization approach to improve upon. And in our case, we used, in the context of CT, we just used the pseudo-inverse. Yeah? So if you have an inverse problem for which a pseudo-inverse of capital T exists, then this would be one example. Yeah? So just compute those bad guys by computing reconstructions via the pseudo-inverse. All right, so I have my data set of good guys that I call PU. And I have the samples from the bad guy samples that are distributed with respect to PN. Okay, and I have a finite amount of samples from each of these distributions, PU and PN. This is somehow the idea. Yeah? And how do I now turn this into a criterion for the regularizer? And this is where we used we got inspiration from what people are doing to train generative adversarial networks, where they are using the Wasserstein distance as an evaluation criterion. So here the idea is, if you just look at this, we are training the regularizer. If you feed the regularizer with samples from the bad guys, the regularizer should be large, so we are maximizing here. And if you feed the regularizer with samples from the good guys, the regularizer should be small. So this is where we have a minus sign here. And we gain some regularity through using the Wasserstein distance here as well, through the criterion that we are optimizing over R's that are 1 Lipschitz. Okay, so this is what we use as a criterion. And where do neural networks come in? Neural networks come in through how we are now parameterizing this R's that we are optimizing over. Okay, so this is the idea. We're not going to optimize now over all 1 Lipschitz functions, but we are optimizing now over R's, which can be represented as convolutional neural networks, basically. Okay. Okay, so 2 quick things. First of all, what the interesting thing about this is that if we train a regularizer like this, the data set of good guys and the data set of the bad guys don't need to be related to each other, right? Because we are not comparing pairwise samples from PU and PN. And so this means, in a way, this is an unsupervised way to train a regularizer, because we don't need ground truth from the inverse problem that I'm going to solve. So they don't need to be paired, which is a nice thing for inverse problems, where we very often in the real world don't have ground truth data. The other one is that depending on how I now parameterize these neural networks that I use as a characterization for R, I can get different properties of the regularizer that I can then use to prove things about the variational model. Like, for instance, and this is the work of Schubo, looking at neural networks that are convex, that are input convex, meaning that you get a regularizer that is actually convex in U. Okay, and then I'm going to refer to the convex and the non-convex version in 2 different ways. So I'm going to show you results for the convex and the non-convex version. And then, of course, if I do this then numerically, I'm also pardon the fact that I'm now replacing this 1 Lipschitz functions by neural networks. I'm also putting here the 1 Lipschitz constraint. I'm going to approximate this, and in our case, we put this here as a penalty term. Yeah. Okay. So the recipe basically is we first need to create the training data, so the good guys and the bad guys, and this depends on the inverse problem you want to solve, how you do this. Then we train the regularizer in this fashion we have seen before, and then we deploy. Once the regularizer is trained, we deploy it into the variational problem, and we need to do parameter choice for the regularization parameter alpha, as Chris pointed out before, and then we go ahead and use it and solve the inverse problem. That's the idea, and we can then solve the minimization problem, for instance, via gradient descent or something like this. Yeah? I'm going to refer to the 2 scenarios of the convex and the non-convex version of this regularizer as AR, which is the non-convex version, and ACR for the convex version. Okay, because I'm going to show you some examples now. So the nice thing about having this structure is now that we can prove things, and depending on whether I'm in the non-convex setting or whether I'm in the convex setting, the things I can prove are differently strong. So in the non-convex setting, we can at least prove existence, and we also can prove stability in a weak sense, in this weak convergent sense. If we look at a setting where X and Y are just generic Banach spaces. If we are in a convex setting, then there is more we can do. As you know, there is a reason why people have mostly looked at convex regularizers in the past. And so we can prove existence and uniqueness because we have strong convexity. Remember, actually, I should have pointed this out, but I've added a little L2 squared term to the learned regularizer just to get, in this case, strong convexity, and in the non-convex case to get coercivity. We can also prove stability. Actually, in the convex case, we can prove it in norm, and we can prove actually that what we get is a proper regularizer. In the sense that when the regularization parameter, when the noise goes to 0 and the regularization parameter goes to 0, I'm going to converge to a ground truth solution, to an R minimizing solution. And then, of course, also the variational problem is much nicer to handle since it's convex. Also, approaches with which I solve this variational problem numerically are nicely behaved, and we can prove convergence and so on. Before I actually show you results, one recent thing that we have looked at, and is particularly due to Marcello and Schubo, is two changes in the strategy, basically, of how to train the regularizer. One is that we are now not just taking at the bad guys a static set of images. Yeah? So not just take as the bad guys, let's say the ones that are computed through the pseudo-inverse, but we are making it harder for the regularizer by also updating this set of the bad guys through, and this is again similar to, if people know how generative adversarial networks work, a generator. We also train at the same time with the regularizer. We also train a generator that is now generating solutions, reconstructions to the inverse problem that the regularizer is then trying to improve upon. Yeah. So this is somehow the idea. So here, so the bad guys are updated with this generator. So here we are training two networks, the regularizer as before, but now slightly different optimality criterion, and a generator, G phi, that is now a neural network trained to solve the inverse problem. Okay. And the optimality criterion for those is like this. So on the one hand, we are training again our regularizer R theta with a one Lipschitz constraint. And this is again the one Wasserstein distance, if you remember from before, right? The only difference now is that the bad guys that were static before are replaced by the ones that come out of the generator, right? The ones that take the data samples and compute the reconstruction. And then at the same time, we make the generator always better iteratively. So we make it harder and harder as we go along by optimizing the generator to minimize the sum of those two terms, right? So we want the generator to minimize the residual between the data and the functions that you get if you reconstruct and then apply the forward operator. Okay, so this is again the data discrepancy term, and as well as the regularizer. Okay, and then we solve this min-max problem here in an alternating fashion. Okay, so we solve for the generator, for the parameters of the generator, alternatingly with optimizing over the parameters of the regularizer. And this actually works really well, and I'll show you in a moment. But the results that Schubo got were really, really impressive. And the nice thing about this now is that on the one hand we can make the regularizer better. And this is in particular relevant when we are setting up the regularizer as a non-convex guy, because there we actually, how you initialize the optimization for this regularizer matters a lot. And the generator now really helps to go into the, when you look at the solution landscape of this regularizer, really helps to go into the into those places of this landscape where the regularizer is better. So this is somehow conceptually the idea. And the other one is that because you also trained this generator, you could also, in the end, just solve your inverse problem by computing the solution via the generator, right? So you have this two things that you can now do. Okay. So now examples, and then I finish. So this is going back to, again, sparse tomography. I think I'm only going to show you this, where we looked at the Mayo Clinic OpenCT dataset, the second generation of it, right, Schuber? The second generation of this dataset?
No, this is the first one.
Oh, this is the first one. Okay, this is the first one. Okay. So the first generation of this OpenCT dataset. And we are looking at the sparse view geometry, where, as we had before, we are undersampling in the angular direction. Okay, so we have sparse angular samples, and that's how we reconstruct. And I'm going to show you now the results of this for filtered back projection, total variation regularization, then the AR. But I show you straight away the AR, so the non-convex AR, but with this new training strategy. Okay, having the generator fight against the regularizer, and just the convex ACR, and then compare this with, let's say, the kind of one state-of-the-art approach for using deep neural networks for solving inverse problems in this unrolled fashion, which is called learned module. Okay, and that's supervised. This is also an important thing. So this is a supervised setting. Okay, so what do we get? Oh, this is interesting.
Let's see that before.
Let's see. Ah, okay. Okay, so I think we can do this quickly. So this is the ground truth, yeah, from which we have simulated the sparse CT measurements. This is the filtered back projection. What I'm reporting here at the bottom, by the way, and maybe we can just look at this one, is a quality measure for the reconstruction that always computes the quality of a reconstruction by comparing it with the ground truth. And the first value that you see here is the PSNR, the peak signal to noise ratio. Okay, so the higher this is, the better is the reconstruction. Okay, so this is for the back projection. This is
so what's the
variation.
second number? You got noise PSNR. What's the 0243?
That's so I can mention this as well. So this is the structural similarity index measure. This is another way to evaluate quality.
Sure.
And again, here the higher the better for both of those. Yeah, so these are just two different ways to evaluate the reconstruction. This is total variation reconstruction. So we can see, I mean, for those who haven't seen this before, this is quite a dramatic jump, right? From filtered back projection is 21.6 dB to 29.2 dB with a sparsity promoting regularizer like the total variation. So that's quite a lot. If you then look at what you can gain with the convex version of the adversarial regularizer, you can gain another 1 dB, which is moderate. Yeah? So it's not a super jump, but you get 1 dB, and again, you by constraining the regularizer to be convex, you have all this theory, right? So there is a trade-off between how much you can prove about your solutions and how good you can get. Now, if I forget about convexity, okay, if I forget about convexity and I also use this generator to make the regularizer better, then I can really gain a lot. Yeah? So this is really quite a significant jump. And if I now compare this with a prototypical, with a kind of state-of-the-art supervised deep learning approach, then I mean, the supervised setting is still better, but it's not so much better anymore. Yeah? So it's between the two. Okay, so that's it. A few extensions of this and also open problems that I think are interesting to look at. So first of all, something that, of course, is a very important question is of how well are these regularizers still performing if I train them on one type of data set and then apply them to the other. So from the theoretical point of view, it doesn't matter, right? Because the regularizer is trained in a way that I have well closeness to a certain extent of the variational problem. The problem more is how good is the regularizer still going to be? So and this is an open problem. The only thing that we have are some empirical investigations from Sebastian's PhD thesis, where he looked at, for instance, in this setting here, he was training the regularizer on knees. Okay, this is a fake kind of color setting. So he was training the regularizer on knees and then applied it to abdominal, to lung CT scans. Okay, and that worked relatively well. So here, here you can see the results, and here you can see when you do it exactly the other way around. So you train on the lungs and then you apply it to knees. So this works well. He also did experiments, and this goes back to what you were asking about, Chris. So because we trained a regularizer independent of this regularization parameter, right? I mean, we train it, of course, on one kind of noise level through the fact that the bad guys will show a certain noise level, right? But otherwise, this does not come up. And so here, what he did was he trained the regularizer on high noise training data, and then applied it to low noise. So on the left, on the left is the low noise, on the right is the high noise, and so this actually worked quite well. Where, and this is maybe also conceptually natural, if you do it the other way around, you train it on low noise and then apply to high noise, then there is a problem because it didn't see this more extreme artifacts in a way. Yeah. So this is where it doesn't work. This is all empirical anyway. Then one thing that we are actually just finishing at the moment that Shubo is leading on is putting more constraints on the learned regularizer, like for instance having a source condition, which could be nice. Or for instance, training regularizers that fulfill certain invariances or variances, like the work that Ferdier did not for the regularizer, but for a learned unrolling scheme to have in the model that the reconstructions should be independent of how you rotate them, with respect to rotations. Another thing is, of course, that the moment you're making something data-driven, you can also play around with the optimality criterion, and in particular, when thinking about inverse problems, or let's say most of the time, when we look at this in a scientific or medical setting, we do not reconstruct an image so that the PSNR is maximized, that it looks pretty, but we have some task that we want to solve on this image, like a segmentation or something like this. And so one interesting thing here is that if you make this now data-driven, you can also choose the optimality criterion in a task-adapted fashion. And so this is also something that we are working on. Another line of work that Christian Edman is leading is this idea to use invertible neural networks for solving inverse problems to make them scalable for very, very large data. Since invertible neural networks have an advantage with respect to the memory requirements they have in the training. And a last thing that again Shubo is actually leading is this idea to use the convex regularizer, the learned convex regularizer, to do also uncertainty quantification. Okay, so yeah, takeaway messages. The role of deep learning, I think, really is the one of a very powerful adapter, extractor of information from data. And one way you can use this is to determine a regularizer. I really strongly believe in this interaction between data-driven approaches like neural networks and a mathematical framework that we can rely on and that we have some theory for. So this hybrid methods, I think, is really an interesting way to go. And the learned regularizers are one example of those. And then, of course, many open questions, and I've highlighted some of those before. So thank you very much. Thanks a lot.
Right, okay, so I'm not sure how we do it, but are there any questions, firstly, from the remote audience? I think we'll start with the remote audience. Do we have any, I think it's 4 remote audience. If you have a question, could you raise your hand or put it in the chat? Oh, brilliant.
I mean, most of them know this stuff already. Most of the audience does know this stuff as well.
Well, there's nothing wrong with seeing it lots of times. The more times I see it, the more I enjoy it. I'm going to ask a question then. So when I've done a lot of inverse problems working with people like doctors and so on, we use regularizers based on their clinical experience. Mm-hmm. So they're looking for certain features like a lung or a breathing. Yeah. In one case I was doing. And we can build that in. Can you do that through labeled supervised learning in your approach? I
mean, you could do this via this task-adapted fashion, via this task-adapted approach, right? If you can formalize what the doctor tells you in terms of an optimality criterion, then you can do it. I mean, this is very case-dependent in a way, how well you can do this.
That's often, of course, what you do. You show an image to a doctor and they reject some spurious because it goes against their...
You could use doctors to create their training sets, right? They could say, you could do this as well.
I'm doing some stuff like that with hips. And as I say,
I mean, this could be quite nice.
CT beehives. Bees. Difficult, they fly around. Any questions from the floor? Yes.
Yeah, a question about the when you're learning the regularizers, the Wasserstein distance, or I think you used the L. L Lipschitz functions. So when you're using a neural network to sort of parameterize your Lipschitz functions, do you know that your neural network is kind of dense in the space of Lipschitz? So I'm thinking, is it more like?
So this is a really good question. Because in a way, the moment you are, well, there are various steps that you do that take you further and further away from the one Wasserstein distance. So the one are the neural networks. Okay, I mean, maybe asymptotically, if you look at infinite width instances of these neural networks, and asymptotically also take the width, no, not the width, the length, basically. To infinity, then I'm sure there are, but that's maybe more for the approximation theory question. There are denseness properties for one Lipschitz functions or something like this. In particular, if you parameterize these neural networks with there are these one Lipschitz neural networks, for instance, that you could use instead of what I've brutally done with this penalty term. Yeah, so you could do it better, such that you get some kind of denseness argument. But it takes you even further away from that, because the Wasserstein distance suffers from this curse of dimensionality. Yeah. And then if we train it in this very high dimensional space on mini batches, then you're not going to minimize the Wasserstein distance really. You're not really computing the Wasserstein distance between those infinite dimensional distributions that live in this super high dimensional space. So in practice, actually, the Wasserstein distance really serves more as a motivation of how you set up the optimality criterion.
Related to that, how are you computing your Wasserstein distance?
So we really use this dual Kantorovich formulation.
That's how you do it.
Yeah, right. And that's what we optimize, and then.
But that's quite expensive.
I mean, what happens in deep learning is, right, that this is taken over by PyTorch or TensorFlow or something like this, and you do this back projection of the parameters, automated differentiation, and so on. So for that, I mean, one needs to ask Schuber maybe computationally how heavy this is, but it's something that these generative adversarial network people also have done quite a lot to use
deeply interested in
formulation.
These things.
Is it possibly more like an MMD distance then?
This is, as far as I know, it's really an open problem. I mean, there are these papers that show you how you can go from MMD to Wasserstein, right? Which one might need to look at again for this, but it's really not clear what you're actually computing.
My last question, because I think you basically had it on your second to last slide. You were talking about uncertainty quantification. And that's point. So, is there a Bayesian sort of formulation when you're trying to learn the regularizer? I mean, do you kind of interpret this as like a hyper prior or something like this?
Okay. So this is maybe a question towards Shubo. So how this framework of Marcello Pereira is really one where you do this via Langevin diffusion. And there, I don't know, Shubo, is it I think the prior distribution is again the exponential is like a Gibbs prior or something like this in this setting of Marcello.
Yeah, so this posterior has to be log concave density. In that case, you can show this discretized Langevin diffusion converges.
Right, but the prior is like the exponential of the convex regularizer, let's say, right?
Fx plus gx, where both f and g are convex proper and lower semi-continuous, and f should be L smooth. It has to have constant L for the gradient.
Yeah. Okay, but I think it's
the prior then is the prior that you're learning. You're not trying to. Your distribution isn't kind of over all priors.
No, it's one prior.
You learn the prior here, and then
Yeah,
so it's kind of the same sort of setting.
Yeah.
It's like a two-step thing. So you first learn the prior and then try to sample from the corresponding.
Right. So you don't account for uncertainty in the prior.
No.
Any other questions?
Instead of solving the map problem, you want to sample from that distribution.
Any other questions from the floor? Any more from overseas, as it were? Right. Well, thank you very much, Carola.
Thank you.
This is a terrific piece of work. It's obviously been going on for ages and lots more to do. So I look forward to hearing.
Yeah, thanks a lot for coming, everyone.
Yeah, it's still raining hard, guys. For those of you who are not Cambridge, we do have a weather warning, which is very exciting if you're a meteorologist. So when's the next seminar?
Tomorrow.